Hey everyone, welcome back to another CIE A Level Physics past paper video. Today we're going to talk about paper 1-2 from the February-March 2026 paper. So let's jump into paper. Alright, what is the value of the ratio 1 kilometer per 1 nanometers? Okay, so 1 kilometer is 1/10 raised to power 3 meters. And 1 nanometers is 1/10 raised to power minus 9 meters. So when you divide these things, the power on the 10 goes to 3 plus 9, which is 10 raised to power 12 meters. Actually, both are meters, so this wouldn't be this ratio would not have any units. So D is the correct answer. What could reduce systematic errors? So systematic errors can only be removed by finding the source of that error. For example, incorrect calibration. So one source could be incorrect calibration. You could be using some wrong assumptions. For example, air resistance negligible. That could be a wrong assumption in case you have a windy area where you're doing the experiment. Zero errors are sort of like incorrect calibration, but zero errors are also like that. Okay, faulty instruments. If the instruments themselves are faulty, they can introduce a systematic error. So systematic errors are like consistent, repeatable errors that exist in all of your readings in a single direction. Just like zero errors exist either positive or negative at a constant value. So they can be eliminated if you find out that source of error. So averaging and repeating measurements and averaging only affects the random errors, does not affect the systematic error at all. Reducing the sample size does actually cause more problems because it will increase random errors, or increase at least the risk of random errors. So careful calibration of measuring instruments that could reduce systematic errors. A student measures the current and potential difference for a resistor in a circuit. Current is 50 milliamps, 0. plus minus 0.01. Potential difference 500 plus minus 0.1 millivolts. Measurements are then used to calculate the resistance of the resistor. What is the percentage uncertainty in the calculated resistance? So R, we know it's ratio of potential difference to the current. So resistance would be 0.01 over 50 plus 0.1 divided by 500. Notice that the percentage uncertainty is not affected by the prefixes. Percentage uncertainty remains the same. The absolute uncertainty will change if we convert this into amps or volts. So percentage uncertainty is not affected. So this multiplied by 100. So you have, actually we can do like 1 divided by 50 plus 10 divided by 500. So you get 0.04. Basically, what I did was I multiplied the 100 over here and over here in the calculation. Graphs can be used to represent the motion of an object. Which relationship is between the quantity of a motion and a property of a graph is correct? Okay, so when you have a ST graph, displacement time, your gradient is your velocity. Okay. When you have VT graph, your gradient is your acceleration, and your area under the graph gives you net displacement. Okay, so let's see among the options which one is correct. Acceleration is the area under the velocity time graph. No, it's not. The area is the gradient. Acceleration is the gradient of the velocity time graph. This is correct. Displacement is the gradient of the velocity time graph. No. Velocity is the area. No. There is only like one correct. B is correct. The water surface in a deep well is 78 meters below the top of the well. The person at the top of the well drops a heavy stone down the well. Air resistance is negligible. The speed of the sound of the air is 330 meters per second. What is the time interval between the person dropping the stone and hearing it hitting the water? Okay, so first off, we need to find out what's the time it takes for it to reach the end, basically. Okay, so you have 78 meters. So the time, let's call it time t1 to actually hit the water. This is going to be S is equal to ut plus half at squared. Since it is dropped, that means initial velocity is 0. So you have 78 times by 2 divided by 9.81 equals to t1 squared. So t1 would be 78 times by 2 divided by 9.81. This is 3.988. Now we need the time for the sound to reach this thing. Okay, so sound has a fairly constant velocity. So time is equal to S over V. Distance is 78 divided by speed is 330. So 78 divided by 330, this is 0.236. So we add the total time. You have 3.988 plus 0.236. You get 4.2240. Okay, so first you need the time it takes to actually hit the water. Okay, so first we need the time it takes to actually hit the water, and then the time it takes for the sound to reach the person again. So both will be calculated separately. A toy car moves in a straight line. The graph shows the variation with time of the displacement of the car from its initial position. A student investigates whether the forces acting on the car are in equilibrium at 4 different times, t1, t2, t3, t4, at which times are the forces acting on the car in equilibrium. Okay, so in this part over here, velocity is 0, it's at rest. Okay, this is also where the gradient is 0, so this is also rest. This is positive constant velocity. This is constant velocity also. Okay, so from the Newton's first law, you can understand this from the perspective of Newton's first law, so that an object continues to be at rest or move with a constant velocity unless acted upon by a resultant force. Or you could say an object under zero resultant force will continue to stay at rest or move at a constant velocity. So actually all of them, they are in equilibrium, because constant velocity is also a type of equilibrium, rest is also a type of equilibrium. So A. A car travels anti-clockwise along a horizontal circular road of radius 12 meters. Car takes a time of 4 seconds to move from point P to Q. Okay. What is the magnitude of average velocity of the car for the journey from P to Q? Okay. Just like average speed, average velocity is the total or net displacement divided by total time. So total displacement is actually this thing. So if I draw this out just to show, so it's going from P to Q. So this is the total displacement. So we need to find out the magnitude of displacement. So this is 144 plus 144, basically like 12 squared, 12 squared. So 12 squared plus 12 squared. Right? So you have 16.97. Okay? So you have 12 root 2 divided by total time, which is 4. So this divided by 4, this is 3 root 2, which is 4.2, O2. A person is suspended from a rope vertically below a helicopter. Helicopter and a person are stationary above the ground. Okay, so system is in equilibrium. Which force forms the Newton's third law of force pair with the weight of the person? Weight of the person is the gravitational force of the person in the gravitational field. Okay, so basically remember, if you have two masses m1, m2, they both exert gravitational forces on each other, which are going to be equal but opposite in directions, according to the Newton's third law, right? So force of the tension in the rope on the person, it has nothing to do with the Newton's third law. Force of upthrust on the person, once again, nothing. Gravitational force applied by the person on the earth, no. Gravitational force applied by the person on, on the earth, yes, on the earth, yes. On the helicopter, no. It's on the earth, like the gravitational force between this person and the earth. Okay, so weight is essentially the earth force acting on the person, and this is the applied by the person on the earth. Two small moving particles collide. After the collision, the particles move in different directions. What is essential for the total momentum to be conserved in a collision? So remember the conservation principle, that the total momentum remains constant if no external forces act on the system. So no external forces act on the system, or you could also say if the system is isolated. System is isolated. So this is the condition for the conservation of momentum. No external forces act on the system of the two colliding bodies. This is correct, by the way. Okay, no kinetic energy is just for elastic, inelastic. It has nothing to do with essential principle or necessary condition for total momentum to be conserved. Okay. Total, once again, this relates to kinetic energy conservation. This relates to also elastic collision. It's not a necessary condition for momentum conservation. A block 1 of mass 3 kgs is on a horizontal frictionless table. A rope with a negligible mass is attached to the block. The rope passes over a frictionless pulley. This is 3 kgs. Okay, so 3g. Block 2 of mass 1 kg is suspended from the other end of the rope. So this is your g, 1g basically. Weight, by the way, we're talking about weight, not mass. The box accelerates. There will be a tension in this direction, there will be tension in this direction, but they will accelerate downwards. The acceleration of free fall is g. The unit of g is meters per second squared, and the tension in the rope has a unit n. What is the tension in the rope in terms of g? Right, okay, so the tension and acceleration both are going to be the same because they're connected bodies. So you have g minus t is equal to a, and the other one is t minus nothing, basically, t, and since this is frictionless table, there is no friction, is equal to 3a. Okay, so this is plus. So when you add these, since these tensions are already positive, like opposite signs, so we don't need to do anything. So you will have g equals to 4a. Okay, once you have g is equal to 4a, you can find out the tension from either one of these. So T is equal to 3 times by g by 4. So this is 3g by 4. A is g by 4. from this thing. So t is equal to 3a, a is g by 4, so you get 3g by 4. The mass of an object can be determined by its relationship to other physical quantities. Three relationships are shown: resultant force on the object, acceleration of the object, linear momentum of the object, velocity of the object, weight of the object, acceleration of the object. Which relationships are always equal to the mass of the object? Okay, very careful wording over here. Resultant force is equal to mass times by acceleration. So if you do mass times by acceleration, we will get mass. Linear momentum, P is equal to mv. So your m would be P over v. Just like over here, you have resultant force over acceleration. But weight of the object and the acceleration of the object. So acceleration may not be the same as the acceleration due to gravity. Okay? So acceleration of object may not be equal to g. So basically what we are doing over here, your weight is mg divided by a. So if your a is equal to g, then you will get mass from this relationship. If acceleration is not equal to g, then you will not get mass. So 1 and the 2 are only guaranteed to give us mass. Third one is not. Basket is sliding on a horizontal frictionless surface with a velocity of 30 meters per second. A mass of basket is m. Block of mass 2m falls vertically into the basket. The block and the basket then move together with the same horizontal speed. What is the v? So basically, it will utilize a principle of conservation of momentum. Conservation of momentum. So momentum before is m times by 30. Okay. Then after the collision, it's not exactly a collision, but there is a change in momentum of two bodies. System is changing. So this is now going to be m plus 2m times by v. Momentum will stay the same. So you have 3m v 30m. So m gets cancelled. Sorry, this is v. And your v would be 30 divided by 3, which is 10. Two children are balanced horizontally in equilibrium on a plank. Equilibrium implies conditions that resultant force in any direction is 0 and resultant torque or moment in any direction about any point is 0 also. The plank is uniform with a mass of 7 kgs and a length of 3 meters. That means when they say uniform, that means the weight is actually passing through the center. There is a pivot at the midpoint of the plank. So basically the weight will not have any moment about the pivot. Child X has a mass of 20 kgs and its distance x from the pivot. The child Y has a mass of 15 kg and is a distance y from the pivot. What is the ratio? What is the value of the ratio x over y? Okay, alright. So notice that the weight, you have sum of torque or sum of moments. Let's find out. Clockwise, anti-clockwise minus clockwise. So this is your anti-clockwise, this is your clockwise. So anti-clockwise is 20g times by x. So I'll write it in the brackets, minus 15gy equal to 0. Okay, x plus y is 30. Okay, so whether we need this or not, we'll see in a second. So the other side is 0 because they're in equilibrium. You have 20 gx equals to 15 gy. So the g and g get cancelled. X over y would be just 15 over 20, 3 over 4, 0.75. C part. Okay. The diagram shows two ways of hanging the same picture. In both cases, the string is attached to the same points on the picture and looped symmetrically over a nail on the wall. The forces shown are those that act on the wall. So, right, okay. Forces shown are those that act on the nail. The weight of the string is negligible. In diagram 1, the string loop is shorter than in the diagram 2. Which information about the magnitude of the forces is correct? Right. Okay, hold on. If you look at it from the perspective of weight, this is going to be your weight. Weight is going to be the same because we're using the same picture, right? So weight is going to be the same. So if you look at it from the perspective of the weight, these forces, these T's, tensions, are going away from these holes to balance them out. You will have some angle over here. So let's call it theta 1 and let's call it theta 2. Theta 1 is greater than theta 2. Okay. So tension would be 2t cos theta 1, and over here you have 2t cos theta 2. So weight is going to be the equal, right? So 2t cos theta 1 equals to 2t cos theta 2. These are tension 1, and this is tension 2. Right? Okay. Now, 2 and 2 will get cancelled, right? So you have t1 cos theta 1 equals to t2 cos theta 2. Since weight is the same, the net effect caused by these two tensions is still the same. So your R1 would be equal to R2. Okay, sorry, no. R1 would be equal to that. But let's see whether the tensions are equal or not. If theta 1 is greater than theta 2, what can we say about the cosine theta? So cosine theta goes like this. Okay, so as the angle grows, the cosine theta goes lower, right? So cos theta 1 would be smaller than cos theta 2. Okay, so your T2 over T1 cos theta 2 over cos theta 1 would be greater than 1. Because cos theta 2 is greater than cos theta 1, right? So that ratio cos theta 2 over cos theta 1 would be greater, right? Simply. So your T2 is greater than T1. Sorry, I wrote this incorrectly. Wait a second. This was cross multiplied. So this is your 1, this is your 2. So T1 is greater than T2. Yes, okay. Now which one of them satisfies this? This one. Right. The diagram shows 4 metal cylinders submerged inside a container of water. Which cylinder has the greatest pressure on its top surface? Greatest pressure on its top surface. So how do we measure the pressure are at a level rho gh, right? And basically h is the depth or the length or the distance from the top of the from the surface. So the greatest depth would have the greatest pressure. The greatest depth is occurring on C. Three objects cube P, cuboid Q, and cylinder R are shown. The dimensions and the masses of the objects are given in terms of length x and mass m. Which objects have the same density? So density over here, mass over volume, so mass over x cubed. This is 4m over 2x squared, actually 2x cubed, right? So this would be basically 2 times by 2. This is mass m over pi r squared h. Pi r squared h is x over pi. So the pi and the pi cancels out, so this leads to m over x cubed. So it's the p and the r. A small ball is projected into the air from a horizontal ground. The diagram shows part of the path of the ball. The ball leaves the ground at point x and has a kinetic energy of 8 joules. A short time later, the ball is at a point y where it has kinetic energy of 3.5 joules. Point y is at a vertical height of 8.8 meters above the ground. Air resistance is negligible. What is the mass of the ball? So in this we're going to use the conservation of energy. So the change in kinetic energy would be equal to the change in potential energy, or basically you can say the loss in KE will be your gain in EP, the gravitational potential energy. So, what do we do? Simply, we are given 3.5, So loss is initial minus final, and gain in potential energy would be m times by 9.81 times by height 8.8. So you will have 8 minus 3.5 divided by 9.81 times by 8.8. So you have 0.052. B. A boat requires a power P to move through still water with a constant velocity. There is a drag force F acting on the boat. So there is a constant velocity, so this means that the engine force, or the driving force, is equal to the resistive force, which is the drag force. Okay? So that means the power exerted by the engine is equal to the power lost against the resistive force. So P is going to be equal to Fv, and V would be just P over F. Nothing too complicated. When the speed of an object is increased from 10 meters per second to 20 meters per second, its kinetic energy increases by E. What is the increase in kinetic energy of the object when its speed increases from 70 meters per second to 80 meters per second? Okay, so the change in the change in kinetic energy E is from half m 20 meters per second and 10 meters per second. So you have basically 400 minus 100, that is 300. So this is equal to 150 m. Right? 150 m. Now we need to go from 70 to 80. So you have new kinetic energy change. Half. Mass is the same, but you are going from 70 to 80. Okay, so 80 squared minus 70 squared is 1500, so 750 meters, 750 m mass. So when we want to take the you can take it as a ratio basically. So 750 m divided by 150 m. So 750 divided by 150. This is 5 times greater. So 5 times by this. Trains supply coal to a power station. The table shows quantities describing the operation of a power station. Power station average output, number of trains per day, mass of the coal on the train, energy from 1 kg of coal, number of seconds per day in 1 day. Okay. Which expression gives the efficiency of the power stations? Okay. We need a power input or energy input, you could say. Right, so power input is this multiplied by this multiplied by this divided by this. Okay, so energy from 1 kg of coal times by number of kgs of the coal. So 1 and then number of trains per day. So you have E, M, N. So okay, so for first let's write it. Total energy would be, total energy input would be energy from 1 kg of coal times by mass of coal in train and then times by number of trains per day. That would be the total energy input. Okay, so power input would be E or NME divided by S. Okay, so your efficiency would be power output over power input. So power output is P divided by NME S. So PS over NME. Which descriptions of objects undergoing elastic and plastic deformation are correct? Elastic deformation is permanently deformed? No. Is not permanently deformed? Yes. No. Yes. Now let's see on the other side. Is not permanently deformed? No, they are permanently deformed. So these two are correct. So the only option where they're both matching is D. A force F extends the length L of a uniform wire by an extension E. The wire has a diameter D and D obeys Hooke's law. What is the Young modulus of the material in the wire? Okay, so this is stress over strain. Stress is force over extension. Force over extension. Force over area, sorry, my bad, not K. And the strain is the extension over original length. Right? So area, you have pi d squared over 4 because we're given this in terms of diameter. So we plug this right over here. You have FL times by 4 pi d squared times by x. Oh, sorry, E. Okay, so 4FL pi d squared E. So 4FL pi d squared over E. An 8 Newton weight is attached to a lower end of the spring, which is fixed at its upper end. The weight is initially held at rest at position X, and the spring is unstretched. Okay, the weight is then released and falls to position Y. and which is 4 centimeter below X. The wave oscillates and then comes to rest at position O, which is 2 centimeter below X. Right, so spring gets stretched, position after initial drop, final position after many oscillations, how much energy is lost from the system. Okay, so to find that, what we do is we need to set up a reference line. This is the reference position. This is the reference position where we will actually find out K. This is your unstretched point, and this is where you will find your K. Because when it is at equilibrium, F is equal to Kx. Right, so at 8 Newton, K, and the equilibrium position, you will have 0.02 meters. So K is basically 8 divided by 0.02, which is times by 100, times by 100. This is 400 Newton per meter. Right, okay. So this is the reference position. So at this point at X, we have some gravitational potential energy. It's 2 centimeters higher than the reference level. So 8 times by 0.02. Over here, it has some some extension. So that means half K X squared. Okay, so the initial, final, that will tell us what is going on. So over here you have GPE, but EPE is basically 0, and so is kinetic energy, right? Over here you still have kinetic energy 0, but you have a drop in gravitational potential energy and some extension also. So 2 and 2. Over here you have no GPE, so GPE is 0, EPE is there, and kinetic energy once again 0. So we just need to find out initial minus final, because it's lost system, right? So initial is 8 times by 0.02 minus 200 times by 0.02 whole squared. So this is 0.08. This. Alright. An electromagnetic wave has a frequency of 3.3 10 raised to the power 14 Hertz. Which principal region of the electromagnetic spectrum is the wave in? Okay, so first off, we need to convert this into wavelength. So speed of light, 10 raised to the power 8 divided by 3.3 10 raised to the power 14 Hertz. So you get 3 divided by 3.3 times by 10 raised to the power 8 minus 14. We times this by 10 raised to the power 9 because we need this in, let's say, nanometers. So you get 909 nanometers. Okay, so you can multiply this with further. Now we know that the visible spectrum goes from roughly about 400 to 700 nanometers. Okay, give or take 50 basically. So like minus 50 plus 50, give or take 50. So right after that, 100 nanometers, 200 nanometers after is going to be infrared. So after red, it's infrared. So this is going to be infrared. A wave on a stretched string causes the particles on the string to vibrate. The diagram shows part of the string at one instant. P, Q, and R particles on the string. Which statement about the two particles of the wave and the two of the particles in the wave is correct? Okay, so this is a stretched string causes particles on the string to vibrate. The diagram shows, okay. Which statement about the two particles and the wave is correct? It is a progressive wave. Particles P and Q vibrate with a phase difference of 90 degrees. P and Q will not have a phase difference of 90 degrees in whether they were stationary or progressive. It would be less than 90 in terms of progressive, and in stationary they would not have any phase difference. So, no. If it's a stationary wave, particles P and Q vibrate with a phase of difference of 90 degrees? Absolutely not. If it's a progressive wave, particles Q and R vibrate with a phase difference? No. If it's a stationary wave, particles Q and R vibrate with a phase difference of 180. So yes, because they're going downwards and they're going up, so they're like 180 degrees apart. And in stationary waves, particles in between two nodes vibrate in phase with each other and out of phase with the adjacent node pair particles. So D. What describes the displacement of a particle on the wave? Distance in a specified direction of the particle from its equilibrium position. Actually, this is the complete definition. Distance in a specified direction, because this is a displacement, from its equilibrium position. So distance and displacement are always measured from a fixed position. In this case, its equilibrium position. Distance moved in a specified direction per unit time, that is your velocity or speed. Maximum distance of a particle from its equilibrium position, that is your amplitude. Product of speed of the wave and time, that is something else. Displacement. That is also displacement. But speed of the wave and time gives you the speed of the displacement of the or distance of the wave. It's not going to give you displacement of the particle. This is actually going to give you distance of the wave. So for example, when t is time period, your s is going to be v times by t. This is going to be equal to lambda. Okay, so in that case, it would be distance of the wave, distance covered by a wave. A beam of vertically polarized light of intensity I0 is incident normally on a polarizing filter. The transmission axis of the filter is at an angle 60 degrees to the vertical. Transmitted light beam is then incident normally on a second polarizing filter. The transmission axis of the second filter is perpendicular to the vertical as shown. The intensity of the light beam that emerges from the second filter is T. So, okay, so this was vertically polarized incident beam, right? So the angular difference between the new axis would be 60 degrees. So I is equal to, let's call it I1, I2, and this is your I0. So I0 cos squared 60. Cos of 60 is 1 over 2. So this is going to be I0 over 4. Then you have wait a second. It is perpendicular to the vertical. So now it's 30 degrees changed again. Okay, not 60, 30 degrees. So this time I2 would be I1 times by cos squared 30. Cos of 30 is under root 3 by 2. So this cos of squared would be 3 by 4. This would be I1 was I0 over 4. So 3 I0 over 60. So 3 by 60, 0.1875. Okay, so 0.1875. So this rounds up to this. A car is driving along a straight road while emitting a sound of constant frequency. There is a stationary observer at each location x, y, and z. From x to y, the car accelerates uniformly from rest up to a high speed. From y to z, the car continues at this constant speed. Which observer will hear the highest frequency of the sound, and what is the position of the car when this frequency is heard by the observer? So the frequency observed depends on the speed of the source. Okay? So what's the formula? V is equal to V plus minus Vs equals to this. from this x, the car is receding, so it will hear the sound of a lower frequency. But these two, they will hear higher frequency. But which one of them would be highest? So it's accelerating between x to y, and then from y to z, it's moving at a constant speed. Okay? So from x to y, it's gaining that high velocity. Okay? So this thing from x to y, y to z, actually this is fine, x to y or y to z. From the perspective of y and z, your observed frequency would be v minus vs. Sorry, vs f naught. F. So it's increasing. The highest one would be heard at z. Okay, so it will be at z when highest observer would be, like the highest frequency observer would be z, and the car would be between y and z, moving at the maximum velocity. Why not others? Let's look at the options. I actually forgot about them. At x, you can never hear that at x because the source is receding, so it can never be that because you will hear a lower frequency at x. At y, but the car is between x and y, so no. It will hear an increasing frequency but not the maximum because the velocity is still increasing. At y, between y and z. So person is at y, observer is at y, but the car is in between y and z. But from the perspective of y, the car would be receding. So it will hear, once again, observed frequency would be lower than the original frequency. So no, only D would be correct. Each diagram shows a stationary wave on a stretched string. Which diagram is correctly labeled? Okay, so first off, let's look at the node and the antinode. This is correct. This is node, but wavelength is not correctly labeled. Over here, node and antinode are not correctly labeled, and neither is the wavelength. Over here, wavelength is correctly labeled, but node and antinode are not correctly labeled. Over here, this is your antinode, this is your node, and this is your wavelength, so D is correct. Two coherent electromagnetic waves are traveling in a vacuum. The two waves meet at a point. At this point, two waves have different intensities. So these are two coherent electromagnetic waves traveling in a vacuum. This means that coherent means constant phase difference. Okay, same frequency, etc. Electromagnetic waves, so same speed. Different intensities. Remember, intensities is proportional to amplitude squared. So they have different intensities, so their amplitudes are different. Which statement about the waves is not correct? They have a constant phase difference. This is correct. They have the same amplitude at the point. This is not correct. So this is it. Laser light of a single frequency is incident normally on a diffraction grating with 5, 10 raised to power 5 lines per meter. A diffraction pattern is formed on a flat screen which is parallel to the grating. The screen is at a distance of 33.5 centimeter from the grating. Distance between the first two order intensity maxima is 15 centimeter. Okay, so you have diffraction grating like this, and this is your screen. This is your first zeroth order, right? Two first order intensity maxima. Okay. This is your first order, this is it, and this is also your first order. Oh no. Okay. So this is your first, this is your first. They're saying that they have a difference of 15 centimeter. Okay. Right. Okay, so basically what we need is this angle, right? So this angle we can find by using trigonometry, because they have given us this distance also. This distance is 33.5. This is 7.5 because half of 15 is 7.5. So we can find out the sine theta. First we get the tan theta. So the angle is equal to tan theta, tan inverse of 7.5 over 33.5. Right? Okay. So we have n lambda d sine theta. This is already per meter. So this is n, not d. Okay. So d would be 1 over 5 10 raised to power 5. Right. Okay. So, okay, we need the wavelength, right? So wavelength would be d 1 over 5 10 raised to power 5. Sine theta, sine would be sine of this angle, tan inverse of 7.5 over 33.5 divided by n, first order, because we're looking at the first order. So d sine theta divided by 1. Okay, alright. So, right, okay. So you have 1 divided by 5 times by 10 raised to power minus 5 times by sine of tan inverse of 7.5 divided by 33.5 double brackets. So your wavelength is coming out to be this. Now we just need to convert this into nanometers. So 10 raised to power 9. So 436.9 or 437. This is going to be the answer. Okay. Which graph represents the variation with current I, or the potential difference V for a filament lamp? So filament lamp, remember the current starts to lower, like due to the heating effect, the current starts to dive down. Okay. So in V over I, this is not IV graph, this is a V over I graph. So in V over I, the resistance is going to increase. So notice, remember we only need the chord, the gradient of the chord or the gradient of the secant. So gradient of the chord, it's increasing. Okay, the gradient of the chord is increasing. Go from here, go from here, go from here, gradient of the chord is increasing. That means the resistance is increasing. So B is the correct answer. What is the definition of the potential difference across a component? This is just work done or energy per unit charge, energy transferred per unit charge, energy transferred per unit time, power transmitted per current, product of current and resistance. No, only A, straightforward, is correct. Conducting putty is a substance that conducts electricity and can be molded into various shapes. The cuboid made from this putty has a length L and width X. The resistance between the square faces of the cuboid is 15 ohm. Some more of the putty is molded into a cylinder that has length L over 2. The resistance between the circular faces of the cylinder is also 15 ohm. So you have circular face, this is the length, this is the length, this has length L over 2. We don't know what the area of the cross section is. The resistance between the circular faces of the cylinder is also 15 ohms. Okay. Over here the area is x squared. What is the radius of the cylinder? Okay. Alright, so let's figure this out. Resistance is resistivity L over A. They're using the same conducting putty, so this is constant. Only the L over A is changing, and so is this R and P are constant. The resistance between the end faces, they're constant. Since they're using the same conducting putty, the resistivity will also be the same. So your L is proportional to A, in fact. So you could use L1 over A1 is equal to L2 over A2. So first we need to find out A2. So A2 would be A1 L2, A1. L2 is L over 2 divided by L1, which is just L. Okay, so you have L and L get cancelled, so you have x squared over 2. So area is pi d squared. No, sorry, we just need the radius now. So pi r squared. So pi r squared is equal to x squared over 2. So your r would be, so let's say r squared would be x squared over 2 pi, and then your r would be x over root 2 pi. So B would be the answer. Each of the Kirchhoff's laws is linked to a conservation of a particular quantity. Okay, this is very straightforward. Kirchhoff's first law is based on conservation of charge, and Kirchhoff's second law is based on conservation of energy. This is something that you should know and should be on your fingertips by now. Eight identical resistors are connected as shown. Ammeter A1 reads 1.5 amps. What is the reading on the ammeter 2? Okay, alright, let's see. 8 identical resistors are connected as shown. So let's say they all have, wait. So we need to figure out, this is 1.5 amps times by R. Okay, so the potential difference across this is 1.5 times by R. Let's say this is your resistance R. This R, all of them have R. So 1.5 R. So we can find out the current flowing through this also. Let's call it I3. So I3 would be V over effective resistance in this particular thing. So this is 1.5 R, because the potential difference across 2R would be the same, and this is your 2R. So you have 1.5 divided by 2, and R get cancelled, so this is 0.75. Okay, so 0.75 current is passing. This is 0.75, right? So this means that the total current passing through the circuit is 0.75 plus 1.5, so this is 2.25 amps. Okay, so 2.25 amps is distributed in these two branches. If we can figure out the potential difference across this combination, we can figure out the current. Okay, so how do we do this? First off, we would actually need the potential difference, effective resistance of this. So 1 over 2R plus 1 over 3R is going to be equal to 6R, 2 times by 3, 3 times by 2. So this is 5 over 6R. So this is your 6R over 5, 6 over 5R. Okay, so potential difference is going to be 6R over 5 times by 2.25. Okay, so 6 divided by 5 times by 2.25 is 2.7. So 2.7 R. Right? Okay. Now that we know the potential difference, we can find out the A2. So A2 would be 2.7 R divided by 2R. So simply 2.7 divided by 2, oh no, divided by 2, this would be 1.35 as it is. Right, okay. You could use the ratio method to find out the ratio of potential differences also, but you would still need the ratio of effective resistances. A battery of electromotive force, EMF, 6 volts and negligible internal resistance is connected in series with a resistor of resistance 6 ohms and a variable resistor of resistance from 0 to 4 ohms. A voltmeter is connected across the variable resistor. The resistance of the variable resistor is changed. What is the range of the voltmeter reading? Okay, so when it is 0, so at 0 ohms. Okay, so if it is at 0 ohms, there is no resistance, so it would be 0 volts, right? But when it's at 4 ohms, okay, so when it's at 4 ohms, this would be 4 over 10 times by 6, so this would be 0.4 times by 6, this is 2.4. So 0 to 2.4. In the alpha particle scattering experiment, a beam of alpha particles is aimed at a thin gold foil. Most of the alpha particles go straight through or are deflected by a small angle. A very small proportion are deflected by more than 90 degrees, effectively rebounding towards the source of the alpha particles. What conclusion about the structure of atoms cannot be drawn from this experiment alone? Okay, so first to actually figure out the negative, we need to figure out what's the actual conclusions from this. Conclusion from this is most of the atomic space is empty. At the center, like the center of an atom, center of atom is dense and positively charged. You could also say most of the atomic mass is concentrated, or most of the density is concentrated at the nucleus. Okay. Most of the atom is empty space. That is drawn from this experiment, conclusion drawn from this experiment. Most of the mass is atom is concentrated in the nucleus. This is basically the same thing. Nucleus contains both protons and neutrons. This is what we cannot determine from this experiment, because the only thing that we could determine about the charge was positively charged, because alpha particles were repelled by the positively charged nucleus. So neutrons cannot be drawn from this. In a type of beta decay, an up quark changes flavor to a down quark, which shows the new hadron created in the beta decay and the sign of the charge on the emitted beta particle. Okay, so in beta negative, you have a neutron converting into a proton plus electron plus electron antineutrino. So this is your 1, 0, 1, 1, 1, minus 1. In beta, so in this case, this is your up, down, down, converting to an up, up, down. That must mean this is the beta particle case, where a proton is decayed into a neutron. This is 0, plus 1, and electron neutrino. So in this case, this is your up, up, D converting into up, down, down. So this is your hadron created is neutron, and this is beta positive. Uranium-238-92 decays into radium-226-88 after a series of alpha and beta minus decays. which will give the correct number of alpha decays and beta minus decays. Okay, so remember, in alpha decay, mass number decreases by 4 each time and proton number decreases by 2. But in beta decay, mass number remains constant, and beta, like for example in beta negative, z becomes actually z plus 1. The new z would be z plus 1. Actually, I should have just written z plus 1. Right? Okay. So, since the mass number remains constant in beta decay, we need to consider the number of alpha particles from the mass number. So, 238 minus 226, and each time 4 are decreasing. So, 238 minus 226 divided by 4, you have 3 alpha particles. Okay? So, this means that the total change in proton number would be from 92 minus 3 times by 2. So 92 minus 6 basically is 86. Okay. Now from the 86, 88 proton number. So we know at each time 1 increases in the beta decay. So 88 minus 86 would be your 2, which is 2 beta decay. So 2 beta particles. So 2 beta particles, alpha particles 3. That is your answer. And that's it for this paper. If you have any confusions, doubts, or questions, feel free to reach out. Furthermore, if you'd like some last minute help for your paper 1 exam, the Grade Booster Pack is available on our Patreon page. The link will be given below in the description also. And furthermore, I'm available through the website also. You could join for the last few days for your exams. You can sign up using this form, or you could find me on Preply, SuperProf, whatever you want to go. Alright, so until the next time, take care. Bye-bye.